Okay, so today we're going to talk about Bernoulli's equation, and that is the second half of the two topics that are included on homework 6. We talked about Euler's equation on Thursday of last week and Tuesday of this week. And so you've already kind of got the background you need in order to solve the first part of homework 6, and then today with Bernoulli's equation, that'll be rounding out the information you need. So as you have questions or concerns or problems over the weekend, or maybe tomorrow, as you're working on homework 6, feel free to reach out. You can send me an email or try giving me a call on Teams, and I'll be glad to speak to you. All right. I wanted to show you a couple of videos I came across that illustrate some interesting characteristics of laminar flow. The civil engineering students who are taking this class saw laminar flow in the lab last week, but the biomedical and the mechanical engineering students who don't take the lab didn't see that laminar flow illustration. So let's look at a couple of videos that kind of demonstrate some interesting properties related to laminar flow. I'll need to pause one of these recordings. Okay, so that's a pretty interesting illustration that shows laminar flow where what we've talked about before is when conditions are laminar, the fluid is slipping without any turbulence and without any interaction with adjacent layers. And I thought that it was really important, this illustration that he did from the top, kind of showing the, let's wait for it to buffer here. He discussed the no-slip condition, how the fluid at the outside edge of the container has the same velocity as the container itself. And then same thing with this inner cylinder. The fluid that's in immediate contact with that inner cylinder has zero velocity. And so then the further away you get from either of those two surfaces is where the velocity is the greatest. And so since he was rotating it really slowly, then the Reynolds number stayed low enough that none of the radial layers were mixing with each other. And so there wasn't mixing outward radially. And then he mentioned the shear thinning. The fact that there were certain times when he was rotating it a little bit faster than others caused the viscosity of the fluid itself to change. And so he described them as striations, or you could kind of see little ring waves. And that was related to the fact that the rotation speed was a little bit different as he was going through it. So that's kind of, I think, an interesting illustration of laminar flow. And let me show you another. This is something that people will often put into their gardens or backyard, just kind of like as a water feature. Okay, so a little bit of explanation. What's happening is that there's a pump in the bucket in the back there that's pumping water into this cylinder. And so this cylinder has a bunch of tubes inside of it, similar to straws. And so what it's doing is it's taking the water towards this discharge nozzle in a really orderly and organized fashion. And then he's careful. Let's see if I can zoom in on the nozzle itself. When he's creating the nozzle, he's very careful to ensure that it's a smooth edge that's been sanded, and so that that doesn't cause any kind of disturbance. And the water is going out at a constant rate, and it forms almost kind of like a stationary arch, and it stays together. All of the fluid has the same velocity, and so it doesn't begin to kind of form droplets as it's falling downward, because it's all has the same velocity through the entire cross section. And it's just kind of an interesting thing. And there is a similar thing to this in the Detroit airport, where they've got a bunch of these set up, and you can see the water kind of dancing around between different puddles, and the streams themselves appear to be stationary over time. Both of those are possible only when the flow conditions are laminar and the velocities are very low. Otherwise, there would be too much turbulence. And so remember that the ways that we've classified flow so far is laminar versus turbulent, uniform versus non-uniform, and steady versus unsteady. Now, each of those different flow classifications give rise to a type of acceleration that's causing it, and then an equation we apply in order to predict the effects of the acceleration on pressure and elevation. And so Euler's equation is what we talked about last Thursday and Tuesday of this week. It's talking about the local acceleration, how the velocity changes with respect to time. And so it could be, for example, a tanker of a liquid that's accelerating over time, or it could be flow through a pipe where the valve is gradually opening and the velocity through the pipe is increasing with respect to time. But either of those examples, the acceleration that we're talking about is local acceleration. And so you used Euler's equation and saw how the piezometric pressure changes in response to an acceleration in the L direction. So here A sub L is talking about the acceleration in a certain direction, and then 2 points that are a distance apart dl, then we're able to find out how there is a change in the sum of the pressure and the gamma z, which is the second component of piezometric pressure. And so remember, the minus sign in Euler's equation tells us that the pressure is increasing in the opposite direction of that acceleration. And then we looked at examples with a variety of fluids, and as the density of the fluid increases, then so does the change in pressure between the 2 points. All right, so that was looking at how local acceleration changes pressure and elevation. Convective acceleration, which is a change in velocity with respect to position, then we have another equation that answers how is that acceleration changing the pressure and elevation, and it's Bernoulli's equation. This is the form of Bernoulli's equation that we will use most often for problem solving. And what it says is that you can pick 2 points, and in this case for Bernoulli's equation, which is location 1 and which is location 2, it doesn't matter in the same way that it really matters in Euler's equation. Remember that when we're applying Euler's equation, we have to be careful about the point 2, as we call it, being the one that would be further to the right if we're applying the acceleration in the x direction. Or if the acceleration is vertically, then point 2 would be the one that has more elevation compared to point 1. In Bernoulli's, the 1 versus 2 isn't an issue. But what it says is that there's conservation between 2 points in the sum of the pressure head, elevation head, and velocity head. So we'll talk about what that means. It comes from applying Euler's equation when you have steady flow along a streamline for an incompressible and inviscid fluid. And so there are 4 basic assumptions that the Bernoulli's equation is built on top of. And like all the equations we're using this semester, Bernoulli's equation is just really a simplification of reality. And its accuracy depends on how close we apply it to the conditions that are assumed. So for example, steady flow. If you try to use Bernoulli's equation and the flow rate is changing over time, then you won't get accurate results, because Bernoulli's equation assumes that the flow in now is the same as the flow in later. So the conditions aren't changing with respect to time. Bernoulli's equation applies along a streamline, and we'll talk more about the specific details of that, but what it means essentially is that, remember, streamlines are those kind of vectors that indicate the direction of flow. And we looked at a picture of smoke going through a wind tunnel, and it was going over the hood of a car and up over the passenger compartment. And from the smoke, we could get an idea of what direction the wind was going, and relatively speaking, where the velocity was increasing. So when you apply Bernoulli's equation, you have to be on the same streamline upstream and downstream. Now these last 2 are especially important. We assume that the fluid that's being calculated for Bernoulli's equation is incompressible. And the 2 fluid types that we use this semester in this course are gases and liquids. And so if you think between gases and liquids, one of them is relatively incompressible and the other is very compressible. And so gases can be compressed quite easily. You've got compressed air in your tires, there's compressed air in a can of hairspray. Compressed gases are very common. And so Bernoulli's equation is trying to predict how a pressure change arises when there's a difference in velocity between 2 points, but it's complicated. If the fluid that you're applying it to can be compressed, then Bernoulli's equation may have some errors. So in other words, if you're applying Bernoulli's equation to water, then you're fine for this incompressible assumption, because water is essentially incompressible. We need absolutely huge pressures for it to begin to compress even a little bit. So it's kind of irrelevant, its compressibility, in the context of Bernoulli equation. Now this final assumption though, an inviscid fluid, what that means is a fluid that has no viscosity. Now there's no fluid that has zero viscosity, but some fluids have a very low viscosity, and for those fluids you're getting close to honoring the expectations of this assumption. So for example, a gas, just like atmospheric air, has relatively low viscosity compared to corn syrup. You know, the fluid that was used in that first illustration with the ultralaminar flow. The reason why he used the corn syrup is because it has so much viscosity, it helps to keep the fluid from mixing. So Bernoulli's equation, if you apply it to a fluid that does have viscosity, it's going to introduce some errors. And the reason why we have this inviscid fluid assumption is because Bernoulli's equation has no way of handling energy losses due to pipe friction. Now, Bernoulli's equation is a model. It's just a conceptual or mathematical representation of reality. And so you can think of models in terms of the small physical representation of a large-scale prototype. Like you can see, here's a Boeing 747 in a wind tunnel, and maybe they are analyzing something to do with the wings or the engines. But the purpose of building a small-scale model like this is so that you can do tests and make changes without having to do that same thing to the full-size prototype. In other words, it's much easier to make small changes to the model than to completely redesign the full-size version of the airplane every time you want to test something. So in the same way, an equation like Bernoulli's equation is a model. It's just a simplification of reality, and it can give us useful information, but it's not a perfect representation of what's really happening in the world. Like this airplane model, it's not a perfect representation of the real thing. You'll notice that this model doesn't have landing gear, and the prototype does have landing gear. The prototype has the tips on the wing. This model doesn't have the tips on the wing. And so the model isn't capturing everything that's happening, but you still can get some important answers to questions by interrogating the small-scale model. And we can do the same thing with an equation like Bernoulli's equation. It may be missing some of the factors that exist in reality, but it still is useful to us, and it helps us to understand what's really going on. So the difference between Bernoulli's equation, which is shown here, and then this formula that I've just brought up is what's known as an empirical equation. And an empirical equation is just derived from observations of reality, whereas a fundamental equation, like Bernoulli's equation, is based on the basic understanding of physics. It's laws that have been known and proven, and so it will be dimensionally homogeneous, where the units on the left and the units on the right are the same, whereas this equation for range just has a bunch of kind of odd correction factors in it, and it's a best fit equation that maybe is useful, but it's not based on any kind of comprehensive understanding of the physics. It's just curve fitting. The boundary of a model is defining the outer limits that apply. And so the boundary is defining where the system is. The system is the fluid and the things that are causing movement of the fluid, for example. The variables are the elements of the system that may be changing, and then the parameters are the constants that don't change. And so in Bernoulli's equation, for example, gamma would be a parameter. It's a fluid constant. G is a parameter, the acceleration due to gravity. But then the variables are going to be the pressure, the elevation, and the velocity. Okay, there are a couple of different ways that we can represent Bernoulli's equation, and we can represent it with units of pressure or with units of length. So it can be written in terms of pressure head, elevation head, and velocity head, or it can be written in terms of pressure, piezometric pressure and kinetic pressure. What it says is that as long as you're applying this analysis along a streamline for a fluid with no viscosity and a fluid that's incompressible and flow conditions are steady, that the sum of these things at one location is the same as the sum of them at the other. And so if you compare what I showed you the first time for Bernoulli's equation, all we've done is the equation on the top is we've divided by gamma. Just because it's sometimes more convenient for us to think of each of these terms with units of length. And so the interpretation is the same. It's just that there's conservation of energy, essentially, between 2 points. That when water's flowing from 1 to 2, if we don't experience any losses, then what's happening is that energy may change form, but it's conserved. So this is the type of application where Bernoulli's equation is used. It's where the velocity is changing due to convective acceleration. So you can see that the velocity upstream is relatively slow at 10 meters per second. The velocity downstream is higher, so that means that in between there was an acceleration. And the pressure of the fluid is going to be changing. And so look at Bernoulli's equation and try and predict when the velocity goes up, what will have to happen to the pressure. Now this nozzle is horizontally oriented. So we could say that if location 1 is the inlet and location 2 is the outlet, then Z1 equals Z2. So what Bernoulli's equation says is that if the velocity is going up, the pressure must decrease. And that's counterintuitive or differing from expectations for a lot of students who look at a nozzle and they'd maybe think, well, if you have more water being forced into a smaller cross-sectional area, doesn't that mean that the pressure will increase? But in fact, the answer is no. The pressure, as the water goes from the left towards the right, the pressure is decreasing. It has to, because more energy is going to be tied up in velocity head at location 2. And that energy has to come from somewhere. And so what occurs is there's a drop in the pressure. We'll do calculations to prove it. Let's look at this expansion in a pipe. Here at location 1, the velocity 5.5 meters per second. So that's a small diameter pipe, and the water's flowing at a high velocity there. And then the pipe expands to a larger cross-sectional area, and that causes the velocity to decrease. So what I'd like you to do is solve for the pressure at location 2 using Bernoulli's equation that's shown on the screen here. Z1 and Z2 are equal, so solve Bernoulli's equation for P2. And of course this is water, as it says in the problem statement, and so the gamma for this fluid is going to be 9810 newtons per meter cubed. So I'll pause for a second. I'd like you to dust off your calculator, go through these calculations and determine what is P2. If you've got a guess, please feel free to put it into the chat box. Alright, so the water is decelerating. It's slowing down with respect to position. There's a convective acceleration acting here. And so Bernoulli's equation is going to tell us how the pressure in the fluid responds to that change in velocity. We're trying to find P2. And so just starting with a little bit of algebra here, just rearranging the equation after we say that the two elevations are the same. If this is my location 1 and this is my location 2, they're both in the middle of the pipe. So I'm following the expectation of Bernoulli's equation that we apply this along a streamline. So Z1 and Z2 are equal, and then rearranging that equation to solve for the unknown P2, you can see what we're going to have is the sum of the energy at 1. So some of the energy at 1 is tied up in the pressure head. You know, it takes a certain amount of energy to pressurize the fluid to 400 kilopascals. And so some of the energy is this potential energy that's in the pressure head, and some of the energy is velocity head, and that's kinetic energy. And so together, P1 divided by gamma plus V1 squared divided by 2G, those two things together, that's how much energy there is at 1. And what we're saying is that if you subtract out the velocity head at 2, then the remainder of the energy is going to be invested into the pressure at 2. So that's the algebra for it. We can do the substitutions now. So we've got the pressure at 1, the unit weight of the fluid, the velocity head at 1 minus the velocity head at 2. Oh, that's too far. So the pressure is 415 kilopascals at location 2. So if you look at this, there's very little energy tied up as the velocity head at location 2. The water's moving so slowly that very little of the energy is in the velocity head. So the pressure increased. It was 400 originally, but some of this energy that was in the velocity head at 1 got transferred into additional pressure at 2. So Bernoulli's equation is just kind of about how energy is changing form between 2 points. Are there any questions related to this example? Now remember, if you were to actually do this experiment in the lab, Bernoulli's equation wouldn't perfectly estimate the pressure at 2. Because in the real world, we wouldn't be applying this in a way that completely satisfies the assumptions made by Bernoulli's equation. For instance, with water, water isn't an inviscid fluid. So the fact that water has viscosity means that there are going to be some losses that occur, some pipe friction losses, and some turbulence when the water is when the pipe diameter is expanding. That would introduce some turbulence. And so the actual pressure at location 2 would be less than this. This is just kind of a theoretical what the pressure at 2 is. But in reality, if you're going to observe it with a pressure gauge, it would be lower than that because of the fact that water doesn't actually, it's not inviscid. Okay, so before we move on, any questions related to this first example? So let's consider this converging nozzle where the pipe diameter is decreasing. If this nozzle is full of water already, and if a fluid like water is incompressible, then what that means is that putting in 1 additional liter of water to the nozzle is going to force out a liter of water from the end. And we call this idea continuity. Continuity says that what goes in must come out. And especially when there's no potential for storage inside of this control volume, if it's already full and you can't add any additional water that's going to be stored, then whatever flows in flows out. An equal volume will go out as was in. Now, in lots of the problems you're going to be solving with Bernoulli's equation, you would be given perhaps the diameter of the upstream and the downstream section. And if you're given the diameter, then you can calculate the cross-sectional area, pi d squared divided by 4. And then if you know the area and the velocity of the flow, that's how you can get the flow rate Q. And so continuity says Q in equals Q out. So flow in equals flow out. And the other way to think about that is that if you multiply the cross-sectional area at 1 and the velocity at 1, then that's going to be equal to the area and cross-sectional velocity at 2. So if the area goes down, the velocity will go up. Right? You kind of already knew that. This is the fancy equation way of calculating precisely how much the velocity is going to increase. But think about what happens when you put your thumb over the end of a hose. What you're doing in a case like that is when the hose is open and unrestricted, the water comes out at a certain speed. But then when you put your thumb over part of that opening, the cross-sectional area is less than it was before you put your thumb on. And now since the area is lower, the velocity increases. And so the jet of water is going to be moving much faster because you put your thumb over the end. So the velocity increases and you can squirt stuff that's further away. So I wanted to point out this continuity relationship because we use it a lot in problems related to Bernoulli's equation. Flow in equals flow out, and specifically A1V1 equals A2V2. Now, here's an example where we're going to use that idea of continuity in order to look at what's happening with the velocities. And this is a combination problem because we have both a converging section, so this is a nozzle where the diameter is decreasing, and we're also connecting a manometer to the nozzle. And the purpose of the manometer is to quantify a pressure difference. What you can see from this manometer, because there's a deflection of 10 centimeters, that tells you that the pressure over here at the opening of the manometer, the pressure is bigger on this side than this opening. So there's more pressure here than there is there, and then that pressure continues through as a gas, and it pushes down on the right side of the U-tube manometer harder than the pressure is pushing on the left side. And so since the pressure is higher over on the right, it deflects the water upward on the left. Now, this example also is showing a stagnation point. So the air is flowing through this nozzle and it's accelerating. The diameter decreases and so the velocity is increasing, but then the air that is right in front of that opening reaches a stagnation point where inside of this tube conditions are static. The air isn't flowing in the tube, it is stopped, it's stationary. Static conditions means that as soon as we turn on the wind through this nozzle, it causes the deflection and then it stops moving. It's not like the water is going to keep flowing until it goes into the nozzle. It's in equilibrium after a certain velocity has been achieved, and then the water stops moving and the air inside the manometer is also stationary. So this stagnation point, these little blue lines, these are the streamlines. And so it shows that there's some air that flows around the stagnation point on either side. But then the streamline that runs right into the opening of that tube, what happens is that all of the energy that was tied up in the velocity head suddenly turns into zero. It had velocity upstream. Downstream there's zero velocity, and so there's a localized increase in pressure. And that's what's causing this deflection, is that the localized increase in pressure at the stagnation point forced the water down on the right. And so that deflection arises because of the transfer of energy from the velocity head to an increase in pressure here at the throat of the nozzle. So what we're going to do for this example is look at Bernoulli's equation between 3 points. We're going to call it point number 1, which is here, point number 2, which is just to the left of the opening, just before the wind encounters that stagnation tube. And then location T is inside the tube, so it's just to the right of that stagnation tube opening. So we're going to use Bernoulli's equation to tell us what is the velocity of the air after this section has converged. So we're going to find V2. And the given information includes the 10 centimeter deflection, and it also includes the fact that the cross-sectional area at location 1 is double the cross-section area, at location 2. So since the area is in half, then that means the velocity doubles from 1 to 2. So you can see that I've said A1 is equal to 2A2. So that means the area upstream is double the downstream area. So that means that the velocity is half upstream compared to downstream. In other words, the velocity at 2 is double the velocity at 1. And this is air that has a density of 1.2 kilograms. So to find what's going on here, we're going to need to combine Bernoulli's equation together with the manometer equation. And you'll notice in the given data, we don't know P1 or P2, or the pressure inside the tube. We don't know the pressures in an absolute sense, but we do know, because of the manometer, the difference in pressure. We know P1 minus PT is causing this deflection. So that is going to be something that we combine together in order to find the pressure at location 2. So it's all on the same horizontal datum. In other words, the elevation at 1, Z1 is equal to Z2 is equal to the Z value at location T. The elevations are the same. So what you should do is rearrange Bernoulli's equation in terms of P sub T minus P1. I'll pause for a second to give you some time to start thinking about this, but the two components are the manometer equation, which tells you how much is PT minus P1, and then Bernoulli's equation. You can rearrange Bernoulli's equation to solve for PT minus P1 as well, algebraically. So let me give you a second to start thinking this through. Okay, so just some preliminary stuff. We know that we're going to be working with air that's flowing through the nozzle, and so we were given the density of air, and by multiplying that by G, we can get the gamma, or the unit weight for air. And then we have the same kind of constants that we know for water, the density and the unit weight for water. And the basic principle here is that at 3 points, at location 1, location 2, and location T, at those 3 locations, the energy is conserved. It's just changing forms. So at location 1, the velocity is slow, so there's going to be a reduction in the if the velocity is slow here, the pressure will be relatively high. And then at location 2, the velocity increases and the pressure is relatively lower. But then inside of the stagnation tube, all of the velocity that was at 2 gets transferred into additional pressure at T. So at all 3 of these locations, at 1, 2, and 3, the energy is equal. It's just changing forms. All right, now the elevations are the same at Z1, Z2, and ZT. The elevations are the same, and so Bernoulli's equation, this full version of Bernoulli's equation, we can cancel out the Z term. And all that's left is the pressure head and the velocity head. The other thing is that, go ahead, is there a question?
I have a question real quick.
Mm-hmm.
I've been the air properties. So it has 1.2 kilograms per meters cubed times 9.81 meters per second squared.
Yep.
You get 11.77 newtons per cubic meter. In water, we do it a little bit different. So, I mean, well, water we know offhand, but wouldn't it be 98.10 newtons per meters cubed? Okay, I see that wouldn't be right.
So
I'm just trying to look at the.
yeah, the unit weight for water is 9810, and then the unit weight for the air, since the density of the air is so much lower, then the unit weight will also be quite a bit lower for the air.
All right.
So we're going to apply Bernoulli's equation. You know, it's air inside here. So when we're talking about like 1 versus 2 versus T, in this Bernoulli's equation, the unit weight we should use should be the unit weight of the fluid that's flowing between those points. And so there's a little bit of water inside the manometer, but it's air that we're analyzing for the flow system. And so here you can see I've simplified Bernoulli's equation by canceling out the velocity head term and removing the elevation terms. So here's Bernoulli's equation, and the gamma that we should use is the gamma of the air. All right, now the manometer equation is what we can use to find the pressure difference between location T and location 1. And the manometer equation is just that the pressure at T here inside of the tube on the right is however much pressure there is at 1 plus, because we're going down through a fluid, plus delta H times gamma. This sketch is better than what I've drawn by hand. So whatever the pressure is at 1 in the center of the tube, what we're assuming is that in something that has as low a density as air, that if you go down like a few centimeters to the water interface, the pressure is the same at the center line of the nozzle as it is at the interface of the air and the water. That's just kind of the assumption we're making, is we don't really even know the diameter of the tube at location 1. And so we're neglecting any pressure change that happens from the center line to the water interface. What we're saying is just that the pressure at 1 is the same as the pressure at this interface, but then as we go down through the fluid, the pressure is increasing because water has a relatively high density compared to that of the air that we were just neglecting. So this manometer equation is talking about how the pressure changes as you go down through this manometer, and then P sub T, the pressure in the tube on the right, so whatever the gas pressure is at the interface of the air and the water is the same. The air pressure isn't going to change through this entire stagnation tube because air pressure doesn't change over the course of a few centimeters in the same way that it will for water. And so the 981 that we've calculated here, 981 newtons per meter squared, that is how much higher the pressure is inside of the stagnation tube compared to what was the pressure at location 1. So that piece of the puzzle is solved with the manometer equation, and then the other piece of the puzzle solved with the Bernoulli equation. Now the Bernoulli equation here is simplified because we've taken out the elevation term and the velocity at t is 0. And what I've just done here is I've multiplied each term by gamma, because here is P sub t minus P1. And I'm going to isolate that on one side of the Bernoulli equation as well, because I know that the pressure difference is 981. So I want to substitute 981 down into Bernoulli's equation. I don't know what the actual pressure is, I just know the pressure difference between the 2 points. And so I took the form of Bernoulli's equation that's in units of head, so each one of these is going to have units of meters, for example, the pressure head term, the velocity head term. And by multiplying it by gamma, now we're talking about Bernoulli's equation in terms of units of newtons per meter squared. So just substituting in the given pressure change of 981 newtons per meter squared, you can see that I rearranged the Bernoulli equation. So on the left side is the pressure difference, and on the right side is density times V1 squared divided by 2. And so the velocity at location 1 is 40.4 meters per second. And then, since we know the ratio of the areas, it told us that V2 would be double the velocity at 1. So if the velocity at 1 is 40.4, then the velocity at 2 would be 80.8. It would be double the velocity at 1 because of the ratio of the areas. Does anybody have questions related to this second Bernoulli's example? All right. Well, just a reminder that your homework assignment that includes some of these Bernoulli's questions is due on Tuesday. So if you get an early start on it now, that'll give you plenty of time to check in it with me if you end up having any questions or run into problems or uncertainty. So that's all I have for you today. Thanks a lot. Hope you have a good day, and I will see you on Tuesday.